this, and we'll pick up on this slide, on current slide. Okay, let me think if there's anything else to talk about. Shakina and I were just talking about how much time we have left. We have this week, we have next week, and I think one more week, and then final exam. Is that what you said? Okay. That sounds right. Okay, so what that means, my question was, do we go on to 20? I didn't put it in the syllabus, but I thought we might have time to do it. But we need to do 2 chapters on light and 1 chapter on relativity, modern physics. Okay? And Sakina said she wanted to do modern physics. Quantum mechanics, no, just kidding. So we will try to hit those 3 chapters, and figuring we'll maybe cover about 1 a week. So, what we'll do now is finish topic 19, and when we finish topic 19, we'll move on to whatever the next topic is in light. We'll start that one, and then at 7 o'clock, we will stop and have our lab on the electromagnetism lab. I don't know if I have that run off yet, but I'll worry about that when I get it. Okay. And hopefully some more will come in. Otherwise, we'll have a fun lab just the 3 hours. I know that class over there is going to hear me talk, so I'll close that door so they can go for it. All right, now my mark here is that we're in 1910, and that's what it says here. Magnetic effect of electrons, the orbits. We had just finished Ampere's law, and I think we've gotten that covered. Okay. Okay, so here we are in 1910. A very good year, by the way. Magnetic effects of the electrons, the orbits. An individual atom should act like a magnet. Why? Because you have electrons going around it, right? Don't you have electrons going around every atom? So why isn't every atom a magnetic atom? Okay? Because the electrons are around the nucleus. Each electron circles the atom once about every 10 to the minus 16 seconds. That's flying, folks. I mean, that's going really, really fast. Of course, it's not going very far because atoms are quite small, but it's still going at an incredibly high rate of speed. That would produce a current of 1.6 milliamps and a magnetic field of about 20 Tesla at the center of the circular path. Now that would be, every electron would do that. Guess what? They don't. Why? The magnetic field produced by one electron in an orbit is often canceled by an oppositely revolving electron in the same atom. So for every electron that you have going like this around an atom, you have another one going like this, so their magnetic fields cancel out. Now, the one exception to that I've never understood is hydrogen. Hydrogen only has one electron. So why in the world is it not somewhat magnetic? I don't know. It's not. Of course, it's a gas. Gases tend not to be magnetic because gases, if you think about a gas atom is doing like this. Okay, anywhere it wants to, flopping around, doing anything it wants to. So every one that you would have like this, the other one could be like this, and they would cancel out each other out too. So yeah, I don't think gases would work too well. They would have to be in a fixed, solid crystal structure. And that, of course, rules out gases. Okay? Now, continuing with that, the net result is that the magnetic effect produced by electrons orbiting the nucleus is either zero or so very, very, very small for most materials, it's not even registerable. You can't even register it. Not measurable at all. Okay? So most of the time that's going to happen. However, there's other things. Electrons also spin. Okay? They also have a spin. The classical model is to consider electrons to spin like tops. Okay? But actually, it's a quantum effect. Now, I don't know if you realize what they mean by quantum effects. This is going to be the stuff we cover in the relativity chapter. I think we'll get there. We may not. We may not quite get there, even in that chapter. But it's a quantum effect, and that's the spin of the electron. Now, I'll go on to the next slide because it's going to describe it better. The field due to the spinning is generally stronger than the field due to the orbital motion. Now, to me, that doesn't make a lot of sense because that orbital motion seems like that would be just like the current going through a loop in a wire, right? But they say the spin is actually stronger. The electrons usually pair up, and most electrons are in electron pairs, okay? And those electron pairs, one spin up and one spin down, so the electrons cancel each other out too. Their fields cancel that out. That is why most materials are not naturally magnetic. Can either of you tell me what three materials are sometimes naturally magnetic?
Nickel.
Yes? Iron. Cobalt. Exactly. Those are three naturally occurring magnetic materials, and none of the rest are basically measurable. In some materials, the spins do not naturally cancel, and such materials are called the ferromagnetic materials. And guess what ferro stands for? Iron. Fe is the symbol, and that's from the Latin, Greek, some sort of word, ferrous, which means iron. The ferromagnetic materials. And that includes iron, nickel, and cobalt, as you said. Large groups of atoms in which the spins are aligned are called domains. And that's actually the title of 19.10 in this book, in the new book, is magnetic domains. So we're just getting to that in this slide, okay? So large groups of atoms in which the spins are aligned are called these domains, okay? When an external field is applied, the domains that are aligned with the field tend to grow at the expense of the others. That causes the material to become magnetized, okay? Now that magnetization could be somewhat permanent or mostly temporary. It just depends. And we'll talk about that a little bit later. Okay? So let's look at how those domains are. In general, those domains, the random alignment shows the unmagnetized material. Every one of these domains is magnetized. Now this is true. These domains exist in iron, nickel, and cobalt. That's all. Okay? And most iron, nickel, and cobalt, this is how the domains are arranged. In every domain, it's a little magnet. However, this little magnet's going that way, there's another one going this way, and that way, all sorts of ways. And this is only in 2 dimensions. 3 dimensions, it gives you even more randomness. So that's usually an unmagnetized material. So iron, nickel, and cobalt, most iron, nickel, and cobalt in their native state is unmagnetized. Okay? However, if you put a magnetic field on that, now all of a sudden, those domains, and I don't know if they blew this up or if it was intentional or they indicate that the domains go together, and if the magnetic field is in this direction, the domains line up generally in the opposite direction. Not totally, there's still a little bit of randomness there, but indeed, most of the domains will line up counter to the magnetic field, okay? Because the north-seeking is going to go toward the south-seeking of that field, okay? Okay, so that's what would happen. Now, if the field is even stronger than it was there, the domains not aligned in the external magnetic field become very small. That slide doesn't make a lot of sense, okay? Because when I look at this slide as opposed to that slide, that one looks a lot more magnetized than this one does. In fact, yeah, I guess what they're saying is, okay, let me back up some now. What they're saying is, and this is not particularly done all that well, they're saying many of these, say a group here, they will line up in this direction. Those that don't line up in that direction are smaller domains. Now they show way more smaller domains pointing opposite that than the few larger domains that are pointing with the field, because this is supposed to be indicating with the field. But if the magnetic field gets even stronger, the B gets stronger here, then bigger domains line up with the field, and the ones that line up counter to the field, they get even smaller, okay? So it's not just the direction of the arrow, it's the strength of the arrow. So in my mind, these arrows should be stronger. If they're that bigger domain, that is indicating a stronger magnetic field this way, and that one's that way, that one's this way, this one's that way, that one, that one. The bigger ones are in this direction, the small ones are counter to that. Over here, more and bigger ones in this direction, fewer and smaller ones counter to that. The stronger the field, the stronger the induced magnetic field in those domains. Frankly, I find that less than, and in the text, you'll see, and this is something, I guess someone must have griped about it before, because in the text, now they make these arrows bigger. They don't make them longer. I think they should make them longer. They make them bigger. This one's bigger, that one's bigger, that one's bigger. If you look in your book on page 644, right at the bottom of the page, these are all about the same size. Those, the ones pointing with the field, are much bigger, bolder arrows. And then when you get to the C, they're really, really bold arrows, okay? They show 1, 2, 3, 4 very strong, bold arrows to the right, a couple that are less bold, and then the ones that are going counter, they're much smaller. So that makes a little more sense than this one does, okay? They must have corrected that. They did in the book. I don't have the new slides. All right, now, we're going to talk about two types of magnets. One of these is we typically call permanent magnets, which means they're not always totally permanent. But these are magnets that, once they're magnetized, they sort of stay magnetized at least for a while. And then the other kind that we'll talk about a little bit later are electromagnets. In fact, we've already talked about those. Those are magnetized only when you put them in a field. And here is Brianna. All right. What's that?
If you don't know how quick, can I get the test?
Which test is that?
5.
5, okay. I'm hoping y'all are the last two that needed it, because I think those are the last two that I got. Okay, let me see if I can find it. Got your test 4. Got your lab 4. So you didn't pick up a test today, you did your lab? It was printed front and back? Huh? Okay. But if you need it, another one, I'll have to make more copies, because that's my last one. What's that? Okay. Well, if you find it and have one blank, turn it back in case that one remaining student does ever show up and needs a copy of it.
You have so much hope in this.
What's that?
You have so much hope in people.
So much what?
No.
Oh, I'm sorry. Okay. So we're talking about domains and permanent magnets. That's magnets that maintain their magnetism after they've been magnetized. Now, remember there's two types of magnetic materials. What are they? hard and soft. Okay? The hard magnetic materials, they're harder to magnetize, but they maintain their magnetism longer. The softer ones, that has nothing to do with hardness of the material, it's just softer magnets. They are easier to magnetize, but then they lose their magnetism more easily. So in the hard magnetic materials, which are basically your nickels and cobalts, and the alloys that have more nickel and cobalt in them, the domains remain aligned after the external field is removed, and they remain there for a longer time. The result is a permanent magnet. In the softer magnetic materials, once the external field is removed, the thermal agitation causes the materials to quickly return to the unmagnetized state. Quickly being the operative word there. I mean, what does it take? Weeks, months, it's not that they permanently stay magnetized. With a core in a loop, the magnetic field is enhanced since the domains of the core align, increasing the magnetic field, but once the magnetic field is turned off of the loop, in other words, the current goes from the loop, then the magnetic field basically goes to, if not zero, goes down pretty drastically. Okay? So that makes what we call an electromagnet. Okay? Now, two types of magnetic materials. Oh, no, I'm sorry. Types of magnetic material. I said it's not two, it's three. Why did this? I just misread it. Ferromagnetic materials. Okay, we've mentioned those. Ferro meaning iron. They have permanent magnetic moments that align readily with an externally applied magnetic field. Those are your iron cores inside electromagnets. You have paramagnetic materials. They have magnetic moments that tend to align with the external magnetic field, but the response is weak compared to the ferromagnetic materials. So there are some other materials that have paramagnetic moments. They're very weak though. And then we have one they call the diamagnetic materials. Externally applied field induces a very weak magnetization that is opposite in the direction of the applied field. Okay? Now that would be something, remember our capacitors, and you put the dielectric in them, right? And the field, the electric field in the dielectric is opposite the direction of the electric field between the plates. Same thing here. You have a magnetic field between two magnets, say, poles of a magnet, going this way, then you have a diamagnetic field induced in the opposite direction. Like a dielectric is with electric field, so a diamagnetic material is with a magnetic field. And that, folks, they just talk about it. They don't do anything more. Okay? There is a very nice little figure on page 645, figure 19.39. And I see only one of you has a book. I don't know if any of you are following on other media. But it's a permanent magnet in red, okay, temporarily magnetizing some paper clips which cling to each other through magnetic forces. Now, some of those are not touching the magnet. They're just touching the end of the other. If you were to break the ones that are touching the magnet, the others lose their field immediately. That would be ferromagnetic, but these readily align with the externally applied magnetic field. Then once the field is disconnected, they lose that magnetism. Okay? They don't say that per se, but that's what it's illustrating. And that, folks, ends topic 19. The summary here, there is no special summary for 19.1 or 2, but 19.3 has several terms and at least one equation in it. There are more terms. You need to read the chapters rather than just count on this. This is just a summary. There's a figure that goes with it. The 19.4 has a fairly short thing, one equation, maybe with a term or two. 19.5 has a figure, definition of magnetic field, field lines, that kind of stuff, an equation and a figure. 19.6, magnetic torque, has, again, the magnetic field and one formula or equation for torque. Ampere's law is 19.7. Several equations there, well, a couple of equations there, and a couple of bold terms or laws that are mentioned. 19.8, magnetic force between two parallel conductors. There's one equation there. And 19.9, magnetic fields of loops and solenoids, a couple of figures there and a couple of equations as well. There are conceptual questions. The odd answers are in the back of the book, so the odd questions wouldn't be bad to look at. And then the problems, again, 19.1 and 2, anything from there is in 19.3, and odd problems 1 through 11 would be appropriate for you to look at there. Those answers are in the back. In 19.4, odds 13 through 21. 19.5, odds 23 through 33. 19.6, odds 35 through 41. 19.7, odds 43 through 53. 19.8, odds 55 through 55 and 57. That's all they've got of that one. 19.9, odds 59 through 63. They don't have any specific ones for 19.10, the ones we just looked at, domains. No problems per se, but there are additional problems, 65 through 75. Not too many of those, but these combine several of the concepts before. Now again, Brianna, we were talking about before whether to go on and try to do topic 20 or not, induced voltages and inductance. It's a good chapter. I wish we had time for it. Actually, a little bit of what we do in the lab will come from that, but I'll describe to you what is going on there. It wasn't in your syllabus because I hadn't been able to cover it in previous time, which was a fairly good time ago that I taught this course, so I skipped it this time. Chapter 21 is alternating current circuits and electromagnetic waves. Another really good chapter, but we definitely don't have time for that one. So we now move, that's a long chapter too, that ends the section on electricity and electromagnetism. So we then pick up in topic 22, reflection and refraction of light. Any questions before we go there? What we'll do is continue on this for, what is it now, 6:10. We'll go for about another 45 to 50 minutes. And at 7 o'clock, we'll stop this chapter and pick up the lab for the last chapter. Okay, so any questions on topic 19? Okay, so what we'll do now is go to topic 22, reflection and refraction of light. A pretty interesting chapter. I think it gets a little bit more interesting (23), but we'll do a little bit here. Okay. So, our topic 22, their chapter 22, reflection and refraction of light. Let's first look at 22.1, the nature of light. Okay? This is called the introduction in the old section, but it's 22.1 in this topic. Light has a dual nature. Okay? Don't know if you've ever thought of it that way. Because when I think of light, I think of electromagnetic energy, period. And yet, it has a little bit of its nature that acts like a particle. And you don't think of energy as being particulate, okay? But it does have a little bit of that. We think of it as being, or I think of it as being more like wave, electromagnetic wave. However, there is a characteristic of it that is particle-like in nature. Wave characteristics, the second one, will be discussed in this chapter, okay? And basically the next chapter. The particulate nature is in the third chapter in this section, which you're not going to have time to do. So, we're just going to focus on the wave nature of light, okay? In this chapter, we'll talk about reflection of light, which y'all are benefiting from right now. Because the light is hitting the board, being reflected off the board, and that's what makes you see it, okay? We'll also deal with refraction of light. And two of you, at least, are experiencing the refraction of light. The two of you with glasses. Because obviously there's something a little bit, I hate to say it this way, off about the shape of your eyeballs, so you don't quite focus as well as you should. So those glasses are refracting the light to make it hit the back of the retina just perfectly, right? But guess what? All of us have lenses in our eyes, and they are refracting light. So it's not just the two of you, all of us are. I have a permanent lens in one eye where I had a cataract removed, and in the other eye, it's my natural one, and it doesn't bend quite as well as it did when it was younger, okay? So one of these days I'll probably need, I do have a small cataract building there, but it hasn't gotten big enough to change. Okay, so these characteristics, reflection and refraction, can be used to understand mirrors and lenses, which are the next chapter, okay? So this one we're just going to look at this, and they do here what they call a brief history of light, which is an interesting way to talk about it. And they call this, and there's a 22.1, that's under nature of light here. The early models of light, it was proposed that light consisted of tiny particles. Hey, quantum mechanics told us that was really right. But early on, we thought that's what light was. Isaac Newton used that particular model to explain reflection and refraction. One thing that Newton didn't get quite right, okay? But it was just a model, okay, that he was using. Huygens came along, and by the way, let me take a time out here and remind you that there is a paper due in this course, and we are in the last month of the course, basically. If you get the paper in this month, you still get one bonus point because the last day of class is in August. Is that right? Did you say? So if you turn it in August, you get 0 bonus points. If you turn it in after that last day of class, you start losing points. So get your papers in, okay? One out of the, how many have we got coming regularly? 4, 7 regularly, 1 paid that we haven't seen yet. I've been in touch with her through email and phone a time or two. I've sent her stuff, but I haven't gotten anything back yet that I've found. It may have come and I haven't seen it yet. But, here's a couple of paper topics. If Newton hasn't been taken already, he would be Huygens is another. Around 1678, which if you think about it in terms of, say, this country's history, 1678, we were colonies then, Okay, that was before, not even sure, let's see, Georgia wasn't even a colony. I think North and South Carolina probably were colonies by then. But he was over in, I think Denmark, no, Netherlands maybe, Huygens, I don't remember. But in 1678, he explained many of the properties of light by proposing that light was wave light, not particle light. Neither one of them were completely correct because light does have this dual nature, wave light and particle light, but Huygens, I think, model fit a little better than Newton's did. Okay? Then came Young, okay, 1801. And Georgia still wasn't a colony yet. Of course, Alabama was just a territory or something, it was part of the whatever was out there. But Young came along, and I think he was British. He gave strong support for the wave theory by showing interference patterns. Okay? And then came good old Maxwell. Okay? Oh, by the way, here, we were a country by then. I'm sorry. 1801, I was thinking 1701. 1801, we had declared our independence. We just had adopted, I think, or in the process of adopting the Constitution. Young came along back in Britain, I believe it was, showed the strong support for the wave theory. Huygens coming out on top of Newton there. Newton long dead, of course. Huygens may have been dead by then, too. And then came Maxwell. Maxwell came along about the end of the War Between the States type time. But he was over in Scotland. James Clerk Maxwell, but it's spelled Clerk. It's pronounced Clark Maxwell. 1865, he proposed electromagnetic waves traveling at the speed of light. Okay, now a couple things there. Number one, that light has a finite speed, it's not instantaneous. Many people were under the impression it was instantaneous. No, it's not. But he proposed these electromagnetic waves. He came up with equations describing those waves long before anyone could measure them. So his was a theoretical model that happened to fit like a glove. About half a century later, maybe not quite that long, finally we had the equipment that we could begin to measure the things and found out Maxwell's equations fit like a glove. Perfect type fit. Okay? At least almost perfect. Okay. And then came Einstein. Oh, Einstein, you had to go mess up our whole picture again. He showed that, indeed, not quite the same way, that Newton's idea of the particle nature of light really had some validity to it. He explained the photoelectric effect. It was a few years later that someone was actually able to measure it, and they said, yuck, he was right again, okay? He used some of Planck's ideas, Planck being a German, I believe it was, physicist who had come up with some of the early quantum mechanics ideas. Einstein built on those and really saw further than any of them had. So there you have a whole passel. I mean, just in this, like 2 or 3 slides here, every one of you could have a different paper topic. And it's, I mean, under Einstein, the particle nature, Einstein himself, the particle nature of light, photoelectric effect, Planck, you know, you could do a couple or 3 things on him. Maxwell, you could write on Maxwell or write on his equations. Young, there's at least 2 or 3 topics probably you could do on him. Huygens, at least 2 on him. Newton, bunches you could do on him. So in those few slides, every one of you could have a completely different kind of paper. Okay, but you don't have to. We cover a lot of other stuff too. So let's go back to Planck again. Okay, well, not quite. Einstein used Planck's idea, and here was that idea of the particle nature of light. The particles, which really aren't particles. You think of particles as having mass. These things don't have mass, okay? Nothing that we can measure. Those particles of light, in fact, I've heard it called before packets of light rather than particles. Little packets of light are called photons, okay? Each photon has a particular energy. And this was Planck's law. What is his name? I want to say Maxwell Planck, but that's confusing the two. Max Planck. Max Planck. Maybe short for Maxwell. Max Planck. And by the way, interesting little story. Maybe it's not interesting to you, but I found it fairly good. Several years ago, I can't think what year it was right now, less than 10, but several years ago, we hosted an Italian kid in our home. We were friends with his parents. His father got his doctorate at the same time my wife got hers, and they were in the program together. They hit it off like crazy. They were, Karen liked to bounce ideas off of him. He liked to listen to Karen's ideas. He was brilliant. Karen, really sharp too. And we enjoyed spending time with them. We didn't know it at the time. We got married within a few months of each other. Of course, they were in Italy. We were here. We didn't know each other then. But so they're just fun people. Okay. And Fabio finished his degree and got a job working for a pharmaceutical company up in Boston area. So he and Rita moved up there. And while in that year that he worked there, lived there and worked there, their first child was born, a son, Giacomo. We didn't get to meet him, we just knew he had been born. And after a year working there, Fabio's parents were putting a huge amount of pressure on them to come home to Italy. So he did. And Fabio was the younger of two boys, and he always tried to do what his parents said. So he went on home, and while they were there, they had two more kids, both girls. And then, I don't know, 6 to 10 years later, he took a postdoc at UAB again, where he had gotten his degree, and came back and did a year's postdoc. And this time he brought Rita and the 3 kids, so we got to meet Giacomo and Camilla and Julia. Julia was like kindergarten age, and Giacomo was late elementary, something like that. Okay. Camilla in between. And then the parents started putting pressure on them again, so they moved back to Italy again. And Fabio got a job at a nearby town at a university, and basically has worked there ever since. And my wife got a chance to do, been invited to, and we kept in touch with them by Skype and emails and various things. Not super close, but we kept in touch. And my wife got a opportunity to give some professional presentation to an international meeting that was meeting in Orvieto, Italy, which is something north of Rome, in a little medieval town that's up on top of a mountain type deal. Really classy place. But it was right near the end of our time between 2 terms. No, it wasn't. It was right near Thanksgiving. That's what it was. And so she went over. Actually, it was a really long trip. She went over like 2 weeks before Thanksgiving, gave the papers at the meeting in Orvieto, and then she had another professional meeting in India. So she went from Italy to India, and she did the time there. We have friends in India also that she visited some with her friends' parents and stuff, and visited there, had their meetings. And then she went back to Italy because that was a round trip ticket there, and that put us there right before Thanksgiving. So I took off for Thanksgiving and flew over and met her, and then we met in Rome and headed to Trieste, where our friends lived there. So we got to go there, and by this time, Giacomo was in high school, and he was like a freshman or sophomore, junior probably. And he was doing quite well at school, and we just had the best time with him. We met the girls too. We never really met them earlier, but all of them were growing up a lot. So we were, and this is too long a story. So anyway, we got along so well with Giacomo, and that his parents were already thinking about it. They didn't tell us this, but they were hoping that he would be able to come to the U.S. because he was technically a U.S. citizen. He was born in Boston, and come over and do his senior year of high school in the U.S. so he would be able to attend a U.S. university because he was a really, really bright kid, a lot like his dad. And then when we got along so well with them, they said, well, maybe why not Birmingham? And they don't have to find a host family and anything else. So over the next year, we started discussing that possibility, and we had enjoyed him so much, we said, sure, let him come. So his senior year of high school, he came over and lived with us. Went to school, a small private school not far from where we live, so it was easy for him to get to. And we had a great year with him. Yeah, he's a high school kid, so there were issues, but nothing serious. And we just had a great year with him. He got sometimes so angry at my wife. He said, "You're just like my mom." That's something my mom would say. She said, "Good, I'm doing my job then." And he would get on the phone and complain, and they would say, "Good, she's doing her job," So we had a great time with him. So he went back to Italy though, because in Italy they have 5 years of high school. So he did his 5th year of high school there. So he graduated from both schools, so he could go either the U.S. or Italy. So he came back and he came back during the spring, and we visited schools with him in the U.S. And he had a free ride at University of North Carolina. I mean, they were going to pay everything. He was that bright of a kid, And we, go for it. Good school, not that far from us, Go for it. But then he got himself accepted at Harvard. And no free ride there, but he got accepted. And he couldn't turn down Harvard. His mother had loved the Boston area. He was born in the Boston area. He felt his heart tug toward it. So he went to Harvard. 4 years, did well. Graduated. We went through his graduation. He came down to visit us a couple of Thanksgivings. So it was a good time. But then he went back to Europe, and he didn't want to work, not at all. So he went to grad school. And he went to Grenoble, France, and worked at a cyclotron doing his research there. But the school that he worked through was the Max Planck Institute, okay? And they have institutes all over Europe. Time out, another story. We have friends from Germany also, very good friends. In fact, we're the godparents of their son. And they were from Munich. And when Olaf's parents came over for their daughter's christening or baptism or whatever, the parents came over. They were living in a small apartment, and so their parents stayed with us. So we became real good friends with his parents. And later, when we went to Karen had meetings in Nuremberg, Germany, they drove up to Nuremberg and drove us back to Munich. So we spent a few days with them. We've been back a time or two since. Long story. Sorry about this. Olaf's parent, Mr. Hans-Jürgen Kutsch, worked at Max Planck Institute in Germany, in Munich, Germany. I don't know if that's the original or the main one, but it was one of the main ones. And he had retired from there, but they lived just one train stop from there, so he drove us over. We took the train up there. He walked us around and showed us a lot of the institute. And we enjoyed being there when we were visiting with him one time. Well, it turned out that's where Giacomo is now doing his doctorate at the Max Planck Institute in Munich, just a few blocks north of where our other friends, and by the way, Giacomo knew I love from here when he was here, so I was good friends with their kids. So anyway, I feel close to Max Planck, even though I've never met him, but I've been to his institute in Munich, and Giacomo is currently there. So, this constant here, Max Planck said, the energy is proportional to the frequency of the wavelength. Remember, Max Planck was saying that the wave nature of light, the energy is related to the frequency of the wave. That proportionality becomes an equation when you put the proportionality constant there, h, and that constant is called Planck's constant. And Planck's constant has an extremely small value, because to get from frequency, which is usually a very high number, to energy, which is a very small amount of energy, that would be a very small constant, 6.63 times 10 to the negative 34th joule seconds. Joule, because energy is measured in joules, frequency is measured in per seconds, so to get this to be energy, this has to be a joule second. So the per second cancel out, and that gives you joules. That encompasses both the natures of light. It interacts like a particle, but it's given a frequency like the wave. So Planck's law, this law, sort of ties the two of those together. It interacts like a particle, but it has a frequency like a wave. Okay. Continuing with this, in some experiments, light acts like a wave, in others acts like a particle. The classical electromagnetic wave theory, that would be Maxwell's laws and that kind of stuff, the explanations of light propagation and interference. And you have experiments that show exactly that. The experiments involving the interference of light with matter are best explained by assuming that light is a particle. The experiments involving the interaction of light with matter best explained by assuming light is a particle, but the classical electromagnetic wave theory shows light acting, propagation, interference, shows acting like a wave. So both of these are true. Light has a number of physical properties. Some are associated with waves, others associated with its particle nature. Okay? Now, the processes of reflection and refraction, remember we mentioned those two, they can occur when light is traveling from one medium and encounters a boundary leading to a second medium. Okay? Now, here's what's happening. And frankly, all of you have seen this, I'm sure. Have you ever looked at a pond or a lake or some body of water, even a pump, okay, that was very, very still? Have you? When you looked at that body of water and say there's trees on the other side, you look at the body of water, don't you see a reflection of those trees in that body of water? Yay or nay? Yeah. Okay? So you're seeing reflection. Okay? But if you were to stick your foot in that body of water, let's say a swimming pool, have you ever done this? Especially if it's very, very quiet, you're the only one in the pool. Stick your foot in and look down at your leg. Your leg looks like it's bent. Or look at somebody else's leg there doing like this in water. It looks like it's bent. That's refraction. In reflection, part of the light bounces off the second medium. The light from the air bounces off the light, the surface of the water bounces off, and you see a reflection. But in a refraction, the light passing into the second medium bends. And that's what makes it look like your leg is bent, but it really isn't. It's the, and you can do this with a ruler and a glass of water. You can do it in many ways, okay? In refraction, the light passing into the second medium bends. Often, both processes occur at the same time. You have some reflection and some refraction. Just about always you do, okay? Not always, but just about. So, we're going to use what they call geometric optics, using ray approximations. The other is wave approximations, and boy, they become sort of a pain to work with. So we're going to do the ray approximations. The light travels in a straight line path in a homogeneous medium until it encounters a boundary between two different medii. Okay? Now, the ray approximation is used to represent beams of light, assuming that light is traveling as a beam. A ray of light is an imaginary line drawn along the direction of the travel that light beam travels. That's your ray. And we're going to use this geometric optics using the ray approximation. All right, here's how it goes. A wavefront is a surface passing through points of a wave that have the same phase and amplitude. Okay? Y'all remember back the very first chapter we did this term. We talked about phase, we talked about amplitudes. Remember that? The first lab was a paper lab. I think I've given it back to you already. Okay? The waves corresponding to the direction of the wave motion are perpendicular to those wavefronts. Okay? So, the rays are straight lines as long as it's one medium perpendicular to the wavefronts and pointing in the direction of the wave motion. So here the rays going that way. Now, if you pictured them as waves, okay, let's just say the peak of this wave would be here, then it goes down, and the peak of the next one would be right there, goes down, the peak of the next one right there. So the wavefronts would be where those corresponding peaks or valleys or any point in that wavefront is moving. A wave is moving. Okay? So the rays are perpendicular to those wavefronts. Okay? And the rays are the straight lines point in the direction of the wave motion. Now they're straight lines as long as you're in a uniform medium and not encountering a boundary. Okay? Now, reflection of light, a ray of light, the incident ray, by the way, travels in a medium, one medium. When it encounters a boundary with a second ray medium, part of the incident wave is reflected back into the first medium. That means it is directed backward into the first medium again. Okay? Now, the light from this bulb up here in this projector is coming down, hitting the board here, and bouncing off and heading toward your eyeballs. That's why you can see, when you look at this, you can see the figure. Okay? When it encounters a boundary with a second medium, part of the incident wave is reflected. This means it is directed backwards into the first medium. Okay. Said that twice, I think. Now, here's a couple of terms that I don't think I ever use in any other context. The first of these is specular reflection. Okay? Specular reflection is the reflection from a perfectly smooth surface. The reflected rays are parallel to each other. So this ray comes down, it hits the surface and bounces off. And these four rays are coming in. The bounce rays are parallel going out because it's a perfectly smooth surface. Now they're going to introduce a little bit later what is happening here. The surface has what we call a normal, which is perpendicular to the surface. Okay? I'm jumping a little bit ahead, but I don't see any reason not to introduce this now. Okay? The line perpendicular to that surface where the medium changes, let me get my pen changed, okay, is the normal line. Okay? At the point of impact, this is the normal, perpendicular to the surface, right? Now, at every point of impact, the angle on this side of the incoming ray, the incident ray, okay, say it's coming in at theta sub I, the incident angle. If it's a perfectly, well, any surface really, the reflected ray is going out at theta sub r. And theta sub I and theta sub r are always equal. Theta r being reflected. So these are the reflected rays. Now that's a pictorial representation of that. And because it's a perfectly smooth surface, the normals are lined up perpendicular, parallel to each other's, okay, then the angle of incidence equal angle of reflection, and they bounce off at exactly the same angle, so the reflected rays are also parallel to each other. All the reflection in this text is assumed to be specular. It's not spectacular, it's specular. Again, I don't think I ever used that word anywhere else. Okay, now this is a figure. They don't really show the surface, or at least I can't see the surface. But I'm going to pick a light color here, maybe this light yellow, and I'm going to try to draw, really poorly, the surface. Okay, and if that's the surface, this is the normal to the surface. Now this is not an illustration, this is an actual ray. This happens to be a laser beam. A laser beam is a monochromatic, that's a red laser, coming in at all the waves there are in sync with each other. They fit a very narrow pattern and they reflect all together. And the angle of incidence, assuming that's coming in from this way, we'll call this theta sub I and this theta sub r. And what we know, and I've jumped ahead, and I apologize for that, but theta I, because this is reflection, is equal to theta r. Those two angles, the incident, and they're always measured to the normal. There's a tendency to talk about this as an angle and that's the angle. Those are not the angles. The angles are always to the normal line. Okay? So I probably should have written here assuming this is the incident ray, the one coming in, and this is the one. So this would be, and this will be the reflected. I'm sorry, I've run out of room. That's reflected over there. Let's go to a red color. What was I going to put here? Oh, we're assuming it's going in that way and going out that way. So the incoming and the outgoing. Incident, reflected. Make sense? All of our reflection we're going to assume to be specular. Now, in reality, not all surfaces are perfectly smooth. I imagine from where you're sitting, I know from where I'm sitting, I can see somewhat a reflection of the light coming in the window off the floor. Can you see it? But no, look at the floor. Don't you see some reflection coming off the floor? But it's not a perfect reflection. It's not got smooth, clean lines like the window does. It has sort of mottled. I see a little bit of green there that represents the leaves, but they're not as sharp as the leaves are up there. In fact, I don't see individual leaves at all. Well, that's because the floor is not perfectly smooth. It's pretty smooth. It's mostly smooth, and especially if they come in and wax it with a real thick coat of wax, it gets even sharper and acts more and more like a mirror. Okay? I can also see the same thing looking at the lights from the overhead lights there. Can you see their reflections off the boards? And you see it's close to being a perfect reflection, but don't you see a little bit of fuzziness on the edges? They're not clean, sharp. I'm talking about those lights there, the bank of fluorescent lights. Don't you see their reflection? And it's not a perfect reflection. pretty good, but not perfect. Here's why. Most of that is diffuse reflection. Okay? Now, in diffuse reflection, what it means, the surface is not smooth, it's rough. Okay? Now, if I were to line up and get so the window should be reflecting off the wall there, I don't see any reflection at all. I can see a reflection off that glass right there. Not a perfect, but pretty good reflection. But off the wall, I can see no reflection at all. Why? Because the surface is like this, a very rough surface. Okay? And guess what, folks? The angle of incidence is still equal to the angle of reflection. The trouble here is that at this point right here, the surface is doing something like that, so that the let me get my color back. The normal line for this angle of incident and angle of reflection is at an angle like this, because at the place it happens to be coming in is a place where it's like this, and the normal line is going like this. Over here, the normal line is sort of like it was on the previous slide. But up here, the normal line is not quite. This line is going like this. So here, your normal line, and the normal line is always perpendicular to that immediate place. So angle of incident equal angle of reflection. But over here, the normal line, that surface is kind of like this. So its normal line is like that. Angle of incident equals angle of reflection. Over here, you got back like this one again. Okay? Angle of incident equal angle of reflection. It's always true, it's just that a rough surface, those normal lines are not parallel anymore, so therefore the reflected rays are not parallel anymore, so you have diffuse reflection. That's the light shining off that wall over there. I can't make out a window anywhere in that, because obviously that concrete wall, even painted, has pits in it, it has roughness on it, it has mortar joints. There's no way that's going to be a perfectly smooth wall. Okay? So anytime that you have enough roughness in the surface, you have the reflected rays traveled in a variety of directions. Even though all the incident rays are parallel, the refracted rays are all over the place. That's what we call diffuse reflection. Okay? And the diffuse reflection makes the dry road seem easy to see at night. Whereas you get a little bit of rain on that, then you get some pretty close to specular reflection. All those lights from the incoming cars are reflecting right up into your eyes. Makes it really hard to see the lines in the road at night. Now, I don't know why they have this figure here. It looks like something other than what I would call diffuse reflection. But I guess that's what they're saying. This is a very rough surface, and so the light comes in, but it gets scattered all over the place, and that's why you see just a whole mass of light going in every direction there. To me, that looks like something else, but we won't get into that now. Okay. I've already snuck up and told you this. This is the law of reflection. Okay? And this is, where are we now? I believe we're, whoops. Before we get to the law of reflection, we got our first quick quiz. I know y'all are happy to hear that, aren't you? Now, figure 22.3. Boy, that is a murky figure if I've ever seen one. Only one of you has a book, and I can't begin to draw it because it's actually a photograph. Okay? So, let's see. 22.3, is that it? Chapter 22. I know in your book, the 10th edition, it's the same one I've got. No, it isn't. No, I'm in the 11th. Yeah. So 10th is more likely, but even the 9th probably has it. Somewhere around 726, page 726, chapter 22 in those books. Look for figure 22.3. Does it show a light car headlights? Probably not. Figure 20, I think you're too far. 22.3. It's not there. Okay, sorry about that. I thought maybe it would be. Okay. You do? Is it a car headlight?
Yeah, 22.2.
Second, 22.2?
Yeah.
Okay, that might be helpful. Is it in yours? Yeah, Brianna? You may not have it. Okay. But here's a quick quiz. Y'all can look on together if you got the picture. Which part of figure 22.3, A or B, better shows specular reflection of light from the roadway? Is that the A one or the B one? And frankly, neither one of them are great, but one of them's a little bit better than the other. Say again? A. I would definitely say A. This is 22.3 A, definitely. Okay? That was quick quiz. And y'all can use the book for the rest of the class. In fact, as far as I'm concerned, you want to use it for the rest of the term. I meant to offer that earlier, but I always had more people here than I had books. Oh, I see. Okay. You have one also?
Yeah.
Okay. Well, then you can just return it at the end of the class tonight. Okay. So anyway, here's the law of reflection, which comes right after that quick quiz. The normal, as I said, is a line perpendicular to the surface. If it's a perfectly smooth surface, then all those lines are perpendicular to that perfectly clear, smooth surface. So the normals are all parallel to each other. If that's the case, the reflected rays are all parallel to each other. So the normal is a line perpendicular to the surface. It is at the point where the incident ray strikes the surface. There's the normal line at that place, and the angle of incidence is equal to the angle of reflection. And they usually call that theta 1 and theta 1 prime. I've been calling it theta I and theta R. The book calls it theta 1 and theta 1 prime. They are equal to each other. Okay? The incident ray makes the angle theta 1 with the normal, and the reflected ray makes the angle theta 1 prime with the normal on the other side, and the incident ray and the reflected ray and the normal all lie in the same plane. That's another given for any type of reflection. Theta 1 is equal to theta 1 prime. What makes the difference between specular and diffuse reflection is the roughness of the surface. If the surface is rough, then the normal lines are not parallel to each other. Okay? And Tia is here. Oh, my goodness, they're coming in packs now.
I made it.
Okay.
Are you happy to see me?
Say again?
Are you happy to see me?
Oh, delighted. Okay. I can't contain myself. Okay. All right. I just barely got here for the last couple of slides before we start lab tonight. So I'm glad y'all are here. Okay. We finished topic 19, and we're skipping 20 and 21 and going straight to 22. We need to cover 2 topics on light and then one on modern physics, which is basically relativity. Okay. Okay. I think we beat the slide to death. Any questions on it before we move on? The angle of reflection is always equal to the angle of incidence whether you have specular reflection, which is perfectly smooth surfaces, or diffuse reflection, which is the incident ray, that reflected rays are in all different directions, okay? But your incident ray, which is theta 1, is always, incident angle is always equal to reflected angle, which is theta 1 prime. Okay. Now, before we start the refraction of light, it's really time to start the lab. Okay. There are a couple of applying physics here that I would definitely tell you, since you've got books at home. Some of you said you did anyway. The colors of water ripples at sunset. Interesting kind of a, I would read that and make sure I understood it. And then double images, you might want to read that as well. There's also example 22.1, not applied physics 22.1, but example 22.1, which shows double reflection of an angled mirror. And it's sort of an interesting problem as well. So we will pick up next time with refraction of light, which is in the new edition 22.2.3, and in the old is 22.2. Okay? So we will end that tonight right there. Okay? And what I have to do is say again? Yeah, and I'm going to. All right, we're getting ready to do. This says it's lab 11. I don't think is that right? I don't know. I don't think the lab number's right. It's like 6 or 7 or something like that. 6 maybe. And it's electromagnetism. 1A. I mean, Roman numeral 1. You don't have to worry with. That was from a previous book, and lots of different things. And this says physical science. This is physics. But we're starting with Roman numeral 2, experiments dealing with electromagnetism. Now, we have here on the circuit board, we have several places where there's magnets. This one's a handy one right here. There's a magnet right there. And I want several of you, you're going to be aluminum. I don't need carbon. You look copper to me, don't you? Okay. You'll be good old iron, lead, and I think that's tin. No, that's nickel. And you'll be tin. And how about you being zinc as well? Okay. I want each of you to come up here, one at a time, paying attention to the others. Aluminum. Touch that magnet and see if it's magnetized. Aluminum, a metal. You think it's going to be magnetic? No. Just right over here. What you say? No. No. Okay, how about copper? Copper's a very good conductor. You think it's magnetic? Let's see. Is he going to be surprised? There's a magnet right here. Uh-oh, maybe that's not a magnet after all. Okay, let's see. Who is iron? What you think? Well, maybe it's not a magnet, though. Hold it up against the side right here. Whoa! Definitely. Okay, iron, yes. Lead. Is the lead out? Okay, I'm sorry. Okay. What you think? Nice heavy metal?
No.
Right here? No. No. Okay, nickel? What you think?
Yes.
Oh, no. Why would nickel? Bright, shiny metal like that? Oh, look at that. And tin. Looks a lot like nickel, doesn't it? What you think? He says no. Along the side right here. Nope. Okay, how about zinc?
Yes.
All right, I left off some. Nope. Okay. Plastic, no, you don't want to try it?
Not really.
Okay. Wood? Styrofoam? Try it. Okay. Hey, you got both of them? Okay, no. Okay. What's that?
For all of them.
Except?
Iron.
And?
Nickel.
No, aluminum wasn't.
Nickel.
Nickel! All right, okay. Well, I didn't have any cobalt, or we would have tested that too. Okay. Now, this next one's going to take a little bit of time, and I'll let y'all help me with it. Okay? Please don't knock these over. That makes such a mess. Take out any old pen. Okay? Take out a pen. They're iron filings. Any pen. No, don't take a nail. It won't work. Take a pen. Okay?
Wait, that's a nail.
No, don't take a nail.
Do I need the styrofoam?
You don't need it. You can leave it. Doesn't matter. Okay? Everybody got one? Okay. Any pen. Okay. Let's start over. I'm gonna get her another one. She flew the coop, huh? That's one back. I got one each. Two. No, what's that? Doesn't have any cell phone. Two. We got three now. So that one I know is not going to work. Three. That's one to her. Three. Right? Three. Yeah. Because there's a real good chance not many of them are going to work very well. Whoops. I hope that wasn't a pin. That's all right. Okay. No, we're not going to do water. It's going to be easier than water. That would be one of these that's not. Maybe neither. Any more? Look at him. Ah, we got you on this. Trying to get out of it. Okay. Two remain. That's keep one back. Okay. I think that's all the pins. I have some other pins and needles, but I don't think they know what they're going to do. Okay, what I want each of you to do, I want you to keep track of it. I'll show you what I want done. Okay. I've got a needle. What I'm going to do is dip it down into the thing. Look at that. That's magnetized. See, I've used so many of these so many times. Most of them are magnetic. So you check each of yours and show me the one that's least magnetized of all the ones you dip in there. Put the point in. Yeah. Okay. So then try it compared to the rest of them. Everybody do theirs. I want the one that's least. Gary? Okay. Which is less? Okay. Compare it to hers. That's pretty much. Check them all and get the one that's least. So far, Brianna's got the least. You look at all the others and say, is that less? What's your reckon? What's your reckon? Okay. Okay. Do all yours?
Mine?
Yeah. He has a magnetic personality.
This one
Is that less than yours?
yeah.
Huh? Less? Is that the least So he's not very magnetic, is he? Okay. So that's the least so far. Hang on to that one. Okay, pass it on down. Y'all compare. Y'all know. Okay. Sam's the least. What you think? Okay, I'll be collecting all those that we know are not the least. None of yours? Who's the least so far? Still has it. Okay. These were not, right?
This whole time.
You surrendering all four of yours then?
That's not that good.
None of yours.
Yours was less than
Thank you. That's right. Who?
hers.
Hers, okay. Okay.
I don't know now.
Courtney's got the least so far. Thank you. And okay, Courtney, look and compare yours to hers.
They're about the same. I don't know.
Okay. Why don't you keep one and the other put it back? Put them all. Okay. And then try the other two. Oh, fell out. All right. You want the Courtney? Okay. Now. Okay. By the way, I can take your plates if you want them. So Courtney was the winner. Oh, breaking hard. No. Okay. So, Courtney, what I want you to do. One more thing. Your point wasn't magnetic. Just check your head. I didn't mean that head. No.
Yeah, a little bit.
A little bit, but not very much, huh? Okay. All right. So her point was a little bit, her head was a little bit, but not that much. Okay. So we're not going to do anymore. We got one that's not magnetized much. If you can find a pen that is not magnetized or weakly magnetized, the least weakly magnetized, that's what she wound up with, then I want Courtney to come up here and stroke it, the point, along the side of this magnet. So stroke the point along the side of the magnet in one direction a few times, as many times as you feel like doing. Now you're only stroking the point, right? Okay. Let's see if you made it any more magnetic or not. Uh-oh, did you see that? Tons magnetized. Okay? Did you increase the magnetism? Okay, then flip it over and do the head. Now, did you stroke the head at all? No. Well, yeah, don't. Okay? Stick it in here and see if the head. Look at that. Was it magnetized like that before? Now, the question is, did you increase the magnetism of the head as well? Yes, big time. If yes, then explain how you increase the magnetism of the head by stroking only the point. How did she do that? Magic?
Electromagnet.
No.
Just ran up to the head.
Okay. What ran up to the head?
Electricity.
No.
Electrons.
No. Okay.
Current.
Magnets are always blank.
Magnetic.
Oh, very nice. Okay.
On. Two.
Poles.
Dipole.
Dipoles. Magnets are always dipoles. If you make one end a magnet, the other end automatically becomes a magnet. So that's your answer to that one. So basically, B1, you could just cross through that. We got plenty more to do. Okay, everybody got number 3 then?
Magnets are always dipoles.
Yeah, magnets are always dipole. Okay. Now, I've got a little compass needle here. This is why I didn't do any water. This is a lot neater. People don't tend to spend it as much. I'm holding it so it's pointing to the north. Will you bring, let's see, what does it say? Use the pin whose poles you determine in 2 above, okay, and determine the north-seeking and the south-seeking pole of that.
So where do I stick it? Here?
Yep, somewhere. No, you stick it somewhere to see if you can make the compass neat. Oh my goodness! What is it doing to the? Can y'all see?
Nope.
Yeah, it's moving the compass.
Which way? The point of the pin. Goodness gracious, she's throwing it all over the floor here. The point of the pin does what to the?
It repels it, so it's
Wait.
the north side.
It wasn't doing that before, was it?
It wasn't.
Okay. Hold it. So you're getting both of them. Yeah. Hold it like this. Now, wait. Do it back in the thing.
Like here?
Yeah. Did you lose some magnetism?
Yeah.
When you dropped it on the floor. See, that's a soft magnet.
Do you want me to like?
Yeah. Do it again. Soft magnets can lose their magnetism when they're... All right,
We're
good. Got it back now. Okay, hold it near. Oh, look at that. What is it doing to the point? Move it around some.
Ah,
The north. So which is the point of that magnet?
it is a north pole.
Is it?
Yeah.
Why?
Because the north is the south.
Say again?
Because the north is the south.
Okay. Which is the north-seeking pole? That's what the question is for. Is it the point or the...
The north seeking is the head.
Okay. Because the point was attracting the north-seeking here, so it must be the south-seeking. So turn that around and do the...
So the head.
Oh, look at that. It's repelling the north-seeking.
The point is the north seeking.
No.
No, the point is
Point
south.
south-seeking because it attracted the north-seeking of the thing. Okay, and flip the point around and do it toward the south. Toward the south. Okay. Okay, the point toward the south. Okay. All right. So, pretty clear that the point was the north-seeking was
Head.
the head, and the south-seeking was the
Point.
point because of what it attracted. Okay, now let's head over to financial services and see if they'll let us in. You can put your We got to find an office with a metal filing cabinet.
I would just use a metal shelf.
Metal chair.
Need a metal filing cabinet. Normally, I would use the office just next door. Let's everybody go to financial services.
Are you going
Turn off the lights and no one will break in. happened? They had this one officer over there who was giving everybody tickets, including the vice president, his boss's boss, vice president. So he, when we merged, they sent him over here. Now, okay, give the contract.
But no, he told me, he's like, as long as you don't pull it your office, but I'm gonna give you a ticket. I was like, how about a pass?
I'm like, well, how am I supposed to park?
They're only $10. Like in my car, it's like
My bucks.
They're so expensive. I need to get a parking spot. It's like a good parking.
See, like, I have 7
You're not even guaranteed a parking spot.
We pay for it.
I
have to give it 2 hours.
See, if you don't get earned that pay, because before 8, really 7:30, you don't get a spot anywhere close. You got to all the way back in.
They took away another parking.
We just don't say it.
Yeah,
Yeah.
have like 2 parking days.
The problem with us is like they have a perfect spot to put a parking deck, but it's historical land, so they don't want to. And they can't tear down these
So
songs.
last semester I had so many tickets to park on the street.
Did it add up to how much a parking pass costs?
I don't even know.
Because you can even get tickets with the parking pass.
You got me too.
Don't they have the buses that take you all the way?
Yeah, but you have to ride the whole route. So your class is
Okay, shame on you, class.
What we do?
Let this old man go down and do that part of the lab without taking his computer with him, so I could have been recording it all. So why didn't y'all say something, huh? You have to watch out for me.
There's only one person missing.
The old gray cells ain't what they used to be, okay?
We can be there on.
What's that?
We can tell them.
I was gonna say, we can tell Megan.
Yeah.
I have amnesia.
Okay. Now, so let's do a quick recap. Y'all did 2A, those whatever it is, 2, 4, 6, 8. Then you B1 didn't have anything really to do, but you did B2, B3, B4, B5, B6, B7, B8, skip 9 and 10, and you did B11. Everybody got it? Even Sam? Okay. Now, the next part, we're coming here to the Toyota board. Now, I got to get one more piece of equipment. I used to use batteries for this, but I found that batteries ran down so quickly when I did it. I started using a power supply because that doesn't run down. Okay. Okay. This cell gets in the way, doesn't it? Okay. Now, what we're going to do is at the Toyota, the name of it is here, the electromagnetism master, station A, right up here. I'm going to plug in the red plug to the red and plug in the black plug to the black. Okay. Now, we'll plug red to red and black to black. Now, one of these is not a good connection. So what we're going to do here, I want one of you to come up here and start turning this knob, reading the voltage as you turn, and somebody else is over here trying to detect to see if you can detect or see any change happening to deflection happening to that compass needle. Okay, and what's going to happen, I'll tell you one or two things. Everybody get up here so you can see it. Okay? one of two things is going to happen. Either the south is going to go to the left end, or the south is going to go away to the left end. You got it? What I think I'll do, if y'all don't mind, just for a moment, let me put some of these away so I don't spill or drop anything. I'll be right back.
How you know a lot of stuff in there? Like paper mache. And they use duct tape. Oh shit. Oh Lord. Wait. Sarah, don't touch nothing else. All of it's gonna fall out though. Because it looks like it's leaning. Yeah. You're gonna have to figure out where they all go. Who?
Nobody? The 10th plate.
Nobody.
Oh, good. Thank you. And you've been bending it all over the place, haven't you? Were you chewing on it?
They didn't move it all. What this is? The compass.
All right. Okay, y'all, we've been recording everything you've been saying here. You know that? Okay. Now, someone's going to start turning that, and notice what happens to the south pole of the compass needle.
Does it need to be closer or?
I'm wondering. Yeah.
I don't see it.
Wait, okay. Let me get a little. Let's try it here.
Whoa.
Turn it all the way off.
Let me know how it.
Oh, wait.
You didn't connect the black to black. This black to black.
Yeah.
Oh my, you're right. No wonder it wasn't working.
Let's
Okay,
try
the other,
this again.
yeah, the other thing is, okay, now try it. Okay, let's stop. Okay, one of these has a bad connection. I don't remember which one it is. Because it should have been deflecting. Try it again. Oh wait, let's try it now. Let me see. This is it. Okay. Turn it all the way down. Okay. Okay, now turn it on. Look at that. You see what's happening? As she turns it up, and it doesn't have to go very high either. Whoa.
It was a short.
I know.
What happened to the needle, Sam? It's gonna blow up.
Yeah, so don't turn it too high. Let's just see the original deflection. Okay, what happened there?
It deflected.
How? You need to give me poles and directions.
We don't see.
There was a north-seeking.
What happens to the compass needle?
We went towards the south.
Okay, the south
Seeking
seeking pole of the compass
was
did what?
attracted to the whatever this is.
Was it? What did it do? Attracted or repelled?
Attracted.
It was.
Mm-hmm.
Okay, let's try it again.
Oh, I'm sorry. I meant the north-seeking.
Okay, the south-seeking pole was repelled by the left end of the coil. Would you agree?
Mm-hmm.
South-seeking pole of the magnet was repelled by the left end of the coil. Everybody buy that? So which is the north pole of the coil? The right or the left?
The left.
Why the left?
No, what?
Because
Would it be the right?
the left was attracted towards the north. Seeking.
So the left was attracted to the north-seeking pole, so that made it a north.
Pole.
So right pole's attracted. Is that what you're saying?
No, I
The
said
new
north
rule-
seeking.
North-seeking.
Mm-hmm.
Well, that's what we're talking about. Okay. Now, as I said before, pay attention to what the south-seeking pole is doing. What is it doing? It's being repelled by the left side of the coil. So therefore, the left, which is the north-seeking pole of the coil.
Oh, of the pole.
Yeah.
See, this just says north pole, not north seeking.
Okay. For everywhere it says that, it's going to be seeking.
Okay.
That's how we distinguish now.
Mm-hmm. It's the right.
It's the right, because the left repelled the south, which meant it was the south. So that meant the right was the north. Very good. Now, what we're going to do is flip the polarity of the inputs. So now the red is on the black here, and let's see what happens here. You want to turn it again? What's happening?
Nothing.
Okay. Look at that. Isn't it attractive?
Mm-hmm.
Okay. Well, you see there, we got it lined up perfectly north, and when we did turn this up some, it attracted the south-seeking pole. So when we reverse the polarity of the input, what happens?
South seeking pole is attracted.
Okay, the question is, are there any changes?
Yes.
Yes, the south-seeking pole was attracted to the left end. Okay. So now what we're going to do is go back to the colors matching. Red and black, not red and green. Okay. Now, at station B, everybody see what we're doing?
Mm.
Plug the wires according to their colors, including two yellow ones. There's the blue one and the green one and the yellow one. They're all made up of ticky-tacky and all. Okay. Now,
On the show weeds.
huh?
Nothing.
Okay. Did she also do it?
Mhm.
Okay. Much later, Bob did. He wrote it up. Okay. What we're going to do is several things now. Station B, I was on the wrong one. Okay. Now, where have we got the yellow wires going to? What you got over there?
Some kind of meter.
All right, some kind of meter. What kind of meter is that?
Amp meter.
Not just an amp meter, a
Voltage.
what? No, not voltage. Amp is amps measures.
Mm.
Amps measure. Oh boy, I saw some good grades coming out of that chapter, and suddenly we don't even know what an amp measures here.
It measures the current.
Current. Okay. So this is not just an amp meter. It's a. See the little symbol in front of it. See the symbol in front of the A.
For the mu.
Mu. And what does that stand for? Microamp meter. So it's going to measure very, very, very small amounts of current. Okay? Now, one person is going to adjust the voltage here. And when you do, also hold this red wire in because that's the one with the bad connection. Okay? Now, we're going to do two things. There's two lights here. Okay? There's a red light, a green light, and a red light. Okay? The only way you're going to see that is for me to turn the lights off. So we're going to have to do this several times. First time we'll do it with the lights off, and someone's going to report what happens to the lights here, and then we're going to turn the lights on and do the same thing again, and you're going to tell what happens to the ammeter. So someone's looking at the ammeter, someone's looking at the lights, someone's adjusting. Okay, what you're going to do, we're going to turn this up, and I'm going to turn it, at least I'm going to start with 9 volts. I'll let you do that. And then what you're going to do is pull this out. And what you'll do is when I say connect, you push it in. Oh, you're going to do the lights, okay. So, so someone come here, and I think it'd probably be better to hold the this in and pull that one in and out. So hold this one in and pull that one in and out. And when you start with it out, okay, and what we're going to do, I'm going to turn it up to 9 volts. You may have to go more than 9, okay? And turn the light off, and when I say connect, you put it in. So you have it close to the hole there. So when I say connect, you can put it in. The light's going to be off. And you're looking at the lights, right?
Mhm.
Okay. No, you're plugging in. Yeah, turn off both lights. Okay, you ready? Turn them off. Connect. Disconnect. Did you see any lights come on?
The green one.
Say again?
The green light came on.
Okay, which way? Connecting or disconnecting? Okay, try it again. Connect. Disconnect.
Disconnect.
What? The green light came on?
Uh-huh.
You didn't see anything on the red. Okay, we're going to turn it up a little bit. Turn on the lights for a second. Okay, yeah, turn it up maybe to, yeah, okay, that's good. Okay? Turn them off. Connect. Disconnect. What you see?
Green on disconnect.
Green on disconnect, that's all you saw?
Mhm.
Okay, let's turn it up a little more.
You're supposed to be seeing the red one apparently.
Yeah.
I guess so.
Okay. Connect.
All right, now there you go.
Wait, it's not connected.
What you do? Yeah, the red one came on.
Disconnect.
The green one came on.
Okay. All right. Now, turn on the light. Your light. Okay. All right. Now, same thing. You look at the microammeter.
Right here.
Connect. Did it do anything?
No.
Disconnect.
This one moved.
Move what? Positive or negative?
Negative.
Okay, do it again. Connect.
Positive.
Positive. Disconnect.
Negative.
Okay. All right. So, at station B, this is number 4. One person should know. Okay, and turn this down. It went up to 18 point what? Around 18 volts. Okay. Okay. At station B, we did 18 volts, red and black wires, and should note the red and green lights at position 2, the other the ammeter readings. Okay. When the first person holds the red to positive and the black to negative. Record what happens to the light and ammeter when you connect it. What happened?
The red light came
Red light came on,
And it was
ammeter went
negative. No, it went positive.
positive. Okay, when the wires were disconnected, what did the lights and ammeter do?
Green and negative.
Green light came on, the ammeter went negative. Okay? Now,
Wait, it went negative. So both of them went negative?
No.
So the first one was positive.
okay, number 4, correct me, red light came on, ammeter went positive. Number 5, the green light came on, ammeter went negative. Okay? Now, Sam's going to reverse the polarity of that. Again, holding the red in place. Okay, holding the red in place, and what we turn it to about 18. Okay. Okay? Turn off the light. Okay, I will. Wait, she's still right. Turn off the, just, okay, you will. Okay, turn off. Okay, pay attention to the lights. Turn off the light. Okay, connect. Disconnect.
Red came on and disconnect.
Okay, try it again. Connect.
Green came on.
Green came on. Disconnect.
Red came on.
Okay, turn on the lights. Look at the ammeter. Connect.
Negative.
Disconnect.
Positive.
Okay,
So it's just the opposite.
just the opposite. Okay, turn off. Okay,
So what was it?
just the opposite. Exactly the opposite. Hold the red on the negative. Right. What happens to the lights in ammeter
So
when
the
you
red.
connect it? Okay, number 6 is connecting. Which light came on?
When it was connecting?
Yeah.
The green light.
Green light came on and the ammeter went
Negative.
negative. And number 7 at the top of the next page. Okay. Go back to number 6. What did you say?
Red light came on
Red light came on 6
and
Yeah.
it was negative.
and the ammeter went negative. Number 7, disconnecting the circuit. The green light comes on
And it's
the
positive.
ammeter went positive.
I thought it was opposite.
And
And
you
you
said it was
just said,
The
No.
opposite of what happened.
I know,
Yeah.
you just said the same.
No, when he connected, red light came on and it was negative. When it disconnected, green light came on and it was positive.
Back at number 4,
That's what you got up top. No,
Back-
it was opposite.
But green light was positive first time.
okay. Back at number 4, when you connected, green light came on. Was that right?
Mm-hmm.
Number 4, and the ammeter went positive.
Yeah.
When you disconnected, number 5, red light came on, and the ammeter went negative. Then when we reversed them on number 6, and you connected the
So, you had it.
I had it wrong.
Wait, okay.
But you said the first time you said red came on and then
Yeah,
green
red
was
came
when
on
it was
first.
connected.
For number
Yeah, but
4.
you
y'all,
said
y'all looked at it. You tell me what happened.
For
Red
number
was-
4, red came on first, right?
Yeah.
Yeah,
And then
so
green,
we-
and then green when you disconnected.
Yeah,
So, okay,
Okay.
number 6. What did you get number 6?
Number 6, I got red light came on and meter was negative.
Okay, and the other one
It was
is green
green
light
came
and
on.
positive.
Wait, for the
Did
second.
your lights change?
Yeah.
No, never mind. For number 6, it was the.
Number 6 is green?
Okay, go ahead.
Okay, that's what I had initially. And then
Okay.
That's right.
green and negative, and the other
For
one's red and
which
positive.
one?
Mm-hmm.
6
which
is
one?
green and negative, 7 is red and
It's
positive.
just opposite.
But that's the same.
That's what I just said.
That's the same. Definitely the same.
It's the opposite of 4.
No, it's
Y'all had it
opposite
right.
of 4 and 5.
Y'all had 4 and 5 right.
Okay, so
4 is red
seven
and
is
positive,
green light
6
came
is
on.
green and negative.
No, it's 5. Oh, 6. Okay,
I'm
that's
looking
good.
at 4 and 6.
Yeah, 4 and 6 are
So
opposite.
7 is red.
Yeah.
Light came on.
4 and 5 are
6
opposite.
is green.
No, 7.
Okay. Wait, no, 4 is red and positive, 6 is green
Oh, wait.
and negative.
I was gonna say, that
It's
is
green, not red.
Red and
That's what I
positive,
had.
meter
Red
was
and red.
positive.
Okay,
Green
and then
and negative.
7 is what? Red
and
and positive. Gotcha.
Okay. Now, before we go any further, it says explain the observation. Everybody got 4, 5, 6, and 7 correct, right? Okay.
Green,
Explain what's happening.
red,
Okay. Here's the deal, folks. You had current through there the whole time, didn't you? When you were plugged in? But you had no light and you had no thing. It was only on connecting and disconnecting. Now, let's take a look at this and see what we were really connecting up here. Everybody want to see it? Sam can see it, and Brianna can see it, but all of you.
See what?
Look at this. If you feel of it, you can probably feel it pretty hot. That's where the juice was going, right? It's not that hot. Okay? Yeah. This hood, not hot at all. So all the current was going through here. But it was only making a change, light change, and ammeter change when you connected and disconnected. And why is that? something we talked about in class. It's only what you were measuring here was a current here that you had no connection to the power source at all. None whatsoever. But when you ran a current through here, you induced a magnetic field. But it's only when that field was changing did you induce a current here. So a changing magnetic field produced a current in the second coil. So that's what was happening.
Induced
Number 8 is a changing magnetic field induced a current in the second coil. And that's what you were measuring with the lights and with the ammeter.
Can you say that one more time?
The changing magnetic field induced a current in the second coil. And really, that's what that chapter 20 was going to do even more of. We didn't get to do it, but we talked about this even back then. Okay. Now, at station C, go back to your red to red and black to black. I'll do red to red here, black to black here. We'll do our ammeter
Yeah.
here,
I had it right.
ammeter there. Okay. Now this time, the coil that's getting the juice is the inner coil, and the outer coil is not getting any. It's doing the changing. Okay, this time we're only going to, what did we go up to last time? 18. This time only go to 9.
So you said the inner core is getting the juice.
Yeah, the inner coil. Yeah. Okay, now hold the red in place and light, camera, action. Okay. Okay.
I'm looking at colors.
You're looking at colors first.
Okay.
Sam will just get out of the way. Okay? Now, so turn off the light, connect, red, disconnect, green, okay? Turn on the light, connect, oh wait, because Brianna's ready.
Oh, hold on, wait, Sam.
Connect.
Okay, one positive, negative.
Okay. It says, at station C, number 9, at station C, place the colored wires in the corresponding plugs. Move the yellow wires we did. Place the red wire on positive in. Okay, we did that. Record the response with lights now on connecting and disconnecting. So connect was
Red positive.
red positive and disconnecting was
Green negative.
green negative. Okay. Now switch the wires.
That's very great.
You did? Okay.
I'm number 8.
I mean, I'm sorry.
That's 9.
That's not big.
Turn off. Okay. Connect.
They're both on.
Okay. You probably jiggle. Pull back out. Connect. What happened? Connect. Okay. Let's cut down the voltage a little bit. Pull them out. Turn on the lights for just a second. Okay. Cut down to, yeah, that would be fine. Okay. Turn them off. Connect.
They both came on.
Really?
Connect again, Sam. Okay, there's the red. There's the red.
Red. Okay. Disconnect.
Green.
Green. Okay. Turn on. Connect.
Negative.
Disconnect.
Positive.
All right.
So,
So you got number
red
10.
negative and green positive.
Connected was red and negative.
Connecting red and negative. Disconnecting
Green and positive.
green and positive. That time we were at what voltage, Sam?
5.7.
5 or 6 volts. A third of what we were before. But I want to ask Brianna a question. Were the lights brighter or dimmer than the previous station?
They were different.
These lights were dimmer than that one. How about the ammeter?
Oh, this was greater.
Oh yeah, the ammeter registered a greater current, and it was the same ammeter, a greater current, even though there was a lower voltage on the input. Huh? This is number 11. Why were the responses at station C greater at station C than at station B, even though B had much more voltage, from twice to 3 times the voltage?
The change in the magnetic field was greater
Why?
because there wasn't as much copper in the second and third coil. I mean,
What he said is not as much copper.
that's what I was thinking.
Okay, so you think less.
Oh, because it was inside.
Oh, because it was inside.
I
Because
didn't know.
yeah, it
We're on the
really,
same page, Sam.
yeah, it really isn't. It is a change in current, but it's really the number of field lines being cut. And you see at station B, it was only the field lines at the end of this coil that were being changing this. Here, all the field lines for the inner core were cutting this one, so a lot more field lines were being cut.
So a lot more field lines are being cut.
Exactly.
Okay.
Number 11, more field lines being cut at C. Because the coil was inside, not end to end.
So how much you hurt? Never mind.
Second?
Nothing.
Okay. Now we're moving to station F. Okay.
Yep.
Okay. Moving to station F. Now, everybody come and look and see. No, we don't need the lights anymore. Sorry. Okay, sorry about that. Someone describe to me what we have at station F.
Station F, we have a magnet.
Okay? With the north up here, south down there.
Mm-hmm.
Okay, that creates a uniform magnetic field there. Right? Going from which way to which way? Which way do the field lines point?
Uniform, they up and down.
Thank you, but which direction? Up or down?
Down.
Down, because they point away from the north toward the south. Right? This is, if you put a little compass needle in there, that's how it would point. Okay? Now, what have you got inside that?
An electromagnet. No.
It's a core. It's a coil, which could be electromagnet. Okay? Which it really is. And what we're going to do is spin that. And we're going to spin it first clockwise, then we're going to spin it counterclockwise. Okay? Now, so let's do that to begin with. Who wants to spin? Okay, Sam is the spinner. Okay? Turn the coil clockwise and the other read the ammeter. What do you see it doing? Anything?
Oh, it's not anything.
Say again? Oh, those don't need to be anything yet. Turn it clockwise. Fast. You see any movement? And which way does it move? Positive. Okay, it's moving slightly positive. Okay? Stop. You can stop now if you want to. Okay? Now, number 13 says turn the coil counterclockwise. Someone else wants to do it? It sounds going to turn again. It goes slightly negative. Now, when it was going, was it steady or was it sort of pulsing a little bit? Pulsing a little bit. So you can put pulse, but it's still positive or negative. Now, I want y'all to look at this connector here sort of carefully. Okay? Oh, man. Okay. Look at that connector. What do you notice about it?
His copper around it.
All the way around it? It goes halfway and then it splits. Halfway splits. Halfway splits. One of these is connected, and what you have connected here is what's going to here, and that's going to the ammeter. So what we're doing by turning that is we're cutting the field lines. Remember we said those are uniform field lines as Sam said, going up and down, okay? And as you turn this, it's cutting a lot of field lines there, not many of them there. Not many. So as you're turning them, that's making a current flow through here. But because that is a special type of connector, okay? And this is what 13 is asking. 14, sorry. Reverse the wires, repeat the turning. What type of connection does the coil have? Do you know what that's called? What did we say it was, Sam?
Electromagnet
the connector there.
split.
You said it's a ring, and I said, is it a solid ring? It's a split ring. Split ring what? Anyone got a clue? I think we talked about it in class. I'm sure we did. I remember the figure on the slide. Split ring.
What does it start with?
C.
Conductor.
No.
Coil.
No. No. Okay.
Coulombs.
Do you remember in mathematics? Yes, you do. When you said A plus B is equal to B plus A. What property do we call that?
Commutative.
Commutative. It's a commutator.
I couldn't have called that.
Okay. It's a split ring commutator. We talked about it in class, or at least I talked about it in class for quite a bit while nobody was paying any attention to me. Okay? A split ring commutator. Commutator.
So split.
Is that the first part of it?
Yeah, the little white there, split ring on top, split ring up here, commutator down there.
Oh, that's just for the first part.
Yeah, before the comma.
C-O-M-M-U-T-A-T-O-R.
A like a communist tater, okay? A commutator, never mind. Okay. Now, what is the result of the split ring commutator?
Cutting of the fields.
Okay, what did you notice about the ammeter?
It was jerky. It wasn't.
Always in one direction, either positive or negative, but it didn't go back and forth. So it made for a pulsed direct current or DC current. Pulsed DC current. That's what the split ring commutator does. Now in the old days, if any of you have a really old car, you have a little generator in the car that turns. And that generator is what recharges your battery. Okay? And it's called an alternator. But it actually is a little generator. But the reason they call it alternator, it alternates every half spin because guess what the battery is? Direct current. Generators produce alternating current. So you have to have an alternator, so every half turn, it flips. Okay, think of the, here would be what would happen if it was really a generator. For half the cycle, it's up, the other half down. Half the cycle up, other half down. What the split ring commutator does, it takes this down half and flips it up. So it does this, and this, and this. Every half spin, it flips it up again. So that is why it's a pulsed direct current. Either all positive or all negative. Depends on which way you turn it. Okay? Now, we're going to go to station G. Okay? Station G. We're going to put yellow to yellow and yellow to yellow. Okay. Now, someone describe to me station G.
That is crazy looking.
What's inside?
It's a magnet
A
inside.
magnet is inside, and you have stationary coils on the outside. Okay? Okay?
Very smart.
Electromagnetic master.
Yeah, Toyota, yeah, they used to
Same
use it
Toyota
to
that makes
teach.
cars?
Huh?
Same Toyota that makes cars?
Yeah. In In fact, the Toyota instructor gave me this. He said, we're not using it anymore. Do you want to have this? Sure.
Some Asian people
Huh?
made it for fun.
Well, yeah, cars are, you've got a battery that starts starts your starter. That takes a lot of juice out of it. So once it's started, you have your alternator recharging the battery. But it has to be direct current, so you used to have a split ring commutator that would make that, what would have been alternating current, pulse direct current to recharge your battery. Nowadays they use what they call a dual diode system. So a diode only conducts electricity in one direction, and as soon as it flips to the other side, then it goes to another diode and sends it in the same direction. So it does the same thing. This time we're turning the magnet inside coils. Before we turned the coil inside a magnet. Okay? Now what happens when it turns it either direction? What do you see happening on the
It's going back and forth.
back and forth? That is what kind of current?
AC.
AC, alternating current. At station G, connect the yellow wires to terminals 8 and 11. I did. Turn the magnet inside the coils. Record the responses of the ammeter.
So both positive and negative.
Yeah, it goes positive, negative, constantly. Back and forth, back and forth. Not strictly positive, not strictly negative. Okay? So what differences do you see from station F?
It's not direct current.
Okay, number one is alternating current rather than direct current. And then why?
Because it
Station.
doesn't have a split commutator.
Yes, station F has a split ring commutator that makes it pulse DC, whereas G does not have a commutator, so it's strictly AC. Number 15 is an alternating current. 16, what difference do you see from those at F? Okay, F was a direct current, a pulse direct current. G was an alternating current. So that's one difference. And the why F had a split ring commutator, G did not. If that makes sense. Yay? Okay. Commutator, and G did not. So F was pulse DC, and G is alternating AC. G did not have a split ring commutator, so therefore it was alternating. Split ring commutator made it pulse DC. So you didn't have one and it remained AC. Red-eyed? Ready?
Oh, it's so late. Goodness
So late.
gracious.
I'm cheating you out of 25 minutes out of your tuition dollars here.
Right.
What's that? Okay. Oh, y'all want your test before you go? Good.
Which one? You just want to select the stack? Okay. I mean, I'm lost. Here's my test. You give it back to the last one. I'm like, wait.
Okay.
Put my name on all of them. I did too. You know what this is?
Looks like part of the.
I would say like the booty or the hip.
Oh, that's good. Oh, yeah, that's a new scalp.
Okay, well,
Looks like a femur or.
I need you to just take my test for me, Sam.
Okay. Hold on just a minute. The copier I use didn't sort either. It's just. Okay. This is chapter 19 test.
Let me get 2 pages.
2 pages.
Oh,
It didn't print it.
Look
Like,
at
okay.
it. It's just-
Moving on now.
better hope y'all can see it.
You too. For some reason,
Make sure you eat your apple.
I didn't have an apple today. Okay, did I give someone 2-page ones? Oh, here we go. They got moved to the bottom. Yours is out of order.
So
Okay, you
this
got page
test
1,
6.
page 2.
Yes.
Okay. Good deal, folks.
Right.
Was the lab helpful?
Yes.
All right, good deal. All right, I'm going to end this